Last time we talked about electronic configuration. That was the last time we touched upon orbitals and on different like electronic states and how electrons behave in the context of an atom or an ion. And we are going to now think about bonding, how electrons will behave if they have any sort of interaction between different nuclei. So there are kind of two extremes and maybe three ways that you can think about bonding. The first way is that the electrons between two different nuclear centers are being shared. So this kind of looks like a linear combination of the two orbitals that you started with. If these were like two hydrogen atoms that bonded together, then they would have started off with two s orbitals. There would be a probability density or a wave function that describes what likelihood the electrons will be at any given point around the nucleus. And they look kind of like balls. If you were to like truncate the like draw a perimeter around 80% probability of where the electrons are, or 90% probability, it would look like a sphere. And if you have bonding, well, the bonded electrons, they're going to end up being equally distributed around each hydrogen. A lot of the time, those electrons are going to be in between the hydrogen nuclei. Sometimes they'll be on one side, sometimes they'll be on another side of either nucleus, but for the most part they're going to be in between. So this is how you think about them, and this is actually called a molecular orbital, or MO for short, instead of an atomic orbital. We're not going to cover that in this class really much at all. Drawing these things is going to be more stuff you see in the next chemistry course, Gen Chemistry, but for our purposes it's good to know what these things are and what the different kinds of bonding mean for different molecules or different compounds. What's the other extreme? So this was sharing of electrons. This is borrowing or taking of electrons. So if we had two atoms that were neutrally charged and one of those atoms takes an electron from the other, then the atom that gained an electron will become a negatively charged ion or anion. So it would have like an extra electron or multiple extra electrons. And the atom that lost an electron or lost multiple electrons would have a positive charge or a multiply positive charge, like 2 plus, 3 plus, etc. And it would be called a cation. So these two ions do not share electrons. There's no shared electrons. There's no overlap of their atomic orbitals. What's happened here is that an electron's been stripped from one and is now being held by another. And they're not being held together by electrons that want to be in between two positive centers. They're being held together by a difference in charge. The positive charge of the cation and the negative charge of the anion will attract each other, just like opposite poles of a magnet will attract each other. So this is an electrostatic interaction. It's positive and negative charges interacting that make them come together or make them like not move terribly apart. And that attraction is weaker than this one. The covalently bonded molecules tend to be more strongly held together. It's harder to break a bond like this than it is to break a bond like this. Water will dissolve this kind of a bond. Water really doesn't dissolve this kind of a bond much at all. Like, it's unusual for that to happen. It happens only in very special cases, and it's not really dissolving. It's stuff like this being broken by water molecules that are forming other bonds like this. So I don't want to confuse you too much. The point is, water just acting with dipole-dipole forces that we'll cover later can break these apart without any sort of without any sort of like meaningful chemistry going on, versus this thing needs chemistry to be broken apart. For sure. Like, I would call anything that can break this apart some kind of chemistry. I would not hesitate to call it this. The electrons would have to be dissuaded from being in this sort of orbital for this bond to be broken, and this requires no change in electrons for this to be broken apart. So in the sense, as I told you at the beginning of the course, the essence of this class is what's happening in valence electrons. There's not really any necessary change in valence electrons for a positively charged and negatively charged anion to be pulled apart. But there does have to be a change in bonding electrons, or like how those valence electrons are being bonded together or participating in bonding before you actually can see this bond be broken apart. Okay, so we got these two extremes: equal sharing, borrowing or theft, no sharing, and then you could have what's called a polar covalent bond. So the sharing thing was called covalent bonding. Ionic bonding is when you have borrowing and no sharing or theft. And here you have something in between where there's unequal sharing. That's called polar covalent bonding. There's still sharing of electrons, but there is a unequal sharing where one of the nuclei is hogging the electrons. The nucleus that is hogging the electrons is going to have a partial negative charge. That's what the delta means. It means partial. And the nucleus that has less of the electron around it, less electron density around it, is going to have a partial positive charge. So it doesn't completely lose an electron, but it does have less of the probability density around it. And if you want to think about this in classical physics terms, you could say that the electron spends less of its time around this nucleus and spends more of its time around this one. So on a time-averaged basis, this thing has more of a negative charge, this thing has a partial positive charge, but not a full charge difference. So the charge difference here is a full electron difference. There's not a full electron difference here. Okay, and this is more of a continuum than I think about it as. So if there's an electronegativity difference between bonding atoms, if there's a very, very, very large electronegativity difference, like if we're talking about a metal and a non-metal involved in a compound together, you would expect that to form some kind of some type. You can figure out what the charges are later, but you would figure it out that there'd be some kind of ionic compound that you'd form from that. A metal and a non-metal, going to be ionic in character. That's a huge electronegativity difference. The metal is very not electronegative, it's electropositive if you want to call it that, and the non-metal is much more electronegative. So that's going to give us an ionic bond. On the other extreme, you could have two atoms that are both nonmetals that are actually the same element. Like you could have two nitrogen atoms. They are going to bond together through covalent bonding because their electronegativity difference is 0. They're the same element. They have exactly the same electronegativity. You could have some sort of intermediate situation like water, where there's a hydrogen that's less electronegative and there's an oxygen that's more electronegative. So the more electronegative oxygen is going to hog electrons in the covalent bonds. Electronegativity, is, as I mentioned last time, has to do with the ability of a nucleus to attract electrons in a bond, in a covalent bond. So what that means, we actually broke this down into a more basic idea of electrons being attracted to a nucleus. And we were saying that atoms or elements in the periodic table that are up and to the right had a higher electronegativity because they would hold their electrons more closely. So that attractiveness of the nucleus as being seen by the outermost electrons is the same attractive force that's going to be leading to higher electronegativity, higher ionization energies, because ionization energies are how much energy it takes to pry that electron out of those outermost highest energy orbitals and away from the nucleus. And the electronegativity is how much those electrons that are being shared are attracted to that nucleus. So it's really high energy electrons around the nucleus. How attractive is that nucleus? How attractive is that nucleus even after you think about all the other electrons that are lower energy that are shielding that nucleus? So it leads to several phenomena, including electronegativity, including ionization energy, including the size of the atom. Like if the outer electrons are more attracted to the nucleus, they are going to be held more tightly and more closely to the nucleus. So as you get higher in the periodic table and to the right, you should be seeing smaller atoms, more electronegative atoms, and higher ionization energies. All because the outer electrons in those elements are more and more attracted to nuclei that either have the outermost electrons in smaller orbitals or have higher effective charges because of only partial shielding by an extra electron for every additional proton that you get by moving from one element to another in the periodic table across a period, across a row. Remember that? Kinda? Yeah? Okay. So like if we were to go to the periodic table, and if we were to go to the periodic table, and if I was to ask you silicon versus phosphorus, which one is more electronegative? Which one would be more electronegative? Phosphorus. Right, phosphorus. Now, if you think about the difference that the outermost electron sees between silicon and phosphorus, the outermost electron in silicon, neutral silicon, sees 14 protons. Remember, that's the atomic number, the number of protons. It sees 14 protons in the nucleus, but it has to see it through a veil of other electrons. So if you're one of 14 electrons, and you're the outermost electron, you're seeing this 14 proton or 14 plus charged nucleus, but you're also seeing these other 13 electrons shielding it or partially shielding it. Fortunately, those 13 other electrons aren't always in front of you, in between you and the nucleus. So, you're only seeing a partially shielded nucleus. And if you go to phosphorus' situation, you're one of 15 electrons looking at a 15 plus nucleus. So the difference is that the nucleus is up like an extra charge of +1, thinking about the perspective of that highest energy electron phosphorus electron versus the highest energy electron silicon nucleus. But the additional electron that you get from going from neutral silicon to neutral phosphorus doesn't completely shield that additional extra proton. So with that in mind, the outermost electron in phosphorus, like one of the highest energy electrons, sees a slightly higher positive charge even through those electrons that come in between once in a while. So the effective nuclear charge, which is what this is actually called, is a little higher going from silicon to phosphorus. So even after you think about all the shielding, all the other electrons getting in the way, you still see more positive charge. So so that means that the electrons are more attracted, like the outermost electrons are more attracted to the nucleus of phosphorus than the outermost electrons are attracted to the nucleus of silicon. So that means that phosphorus is going to be more electronegative than silicon. That's a skill you need to have to be able to tell me about the degree to which something is an ionic ionically bonded compound, or a covalently bonded compound, or a polar covalent compound. You need to know these electronegativities to be able to do that. Tell me about phosphorus versus nitrogen. Which one's going to be more electronegative? Nitrogen will be more electronegative. And the way you think about this is you think about the different orbitals that the outermost electrons will be in. Here it's going to be a 2p orbital. Here for phosphorus it's going to be a 3p orbital. The 3p orbital is a lot bigger. So just because you have these charges being separated by a bigger space on average, it's going to be less attracted to the nucleus. So the outermost electrons of phosphorus are going to be less attracted to the nucleus of phosphorus than the outermost electrons of nitrogen, just because they're further away, on average. So that's all. The bigger effect here is the effect of... not really bigger, the greater effect here is the change in electronegativity going from one row to the next one. So like going down a column reduces the electronegativity a lot more than going across one does. So these periodic trends up and down are much more bigger differences or much greater differences than left to right. Okay, so if I think about water, it's H2O. It's covalently bonded because hydrogen isn't really a metal. It's more of a nonmetal, and oxygen's a nonmetal, so it's going to be covalently bonded. Oxygen is going to be more electronegative than hydrogen, so I would expect for there to be a partial positive charge on hydrogen and a partial negative charge on oxygen that corresponds from the electrons being shared much, much less to the hydrogen than they are to the oxygen. So that's the kind of reasoning you need to be able to do, and the periodic trends need to be there in your mind to be able to do this stuff consistently. This is a depiction of a polar covalent bond. This is trying to show you that there's more electron density around this fluorine than there is around this hydrogen, and I guess what they're showing you is the bonding electrons, hopefully, and not just total electrons, because otherwise this would be kind of a weird thing to show you. But this should be demonstrating to you that there's more electron density around this fluorine. So I think there's some Alex questions about this, like, look at this bond. What does it look like to you? And you're supposed to be able to characterize that if it's unequal sharing, we're talking about a polar covalent bond. Polar indicating that it's unequal, covalent meaning that it's still sharing. Okay, so yeah, electronegativity is just that ability of an atom in a molecule, or sorry, a nucleus in a molecule to attract shared electrons to itself. So if there's unequal electronegativity, then there's going to be unequal sharing. And we already talked about this a lot. You have a good intuition for it, so you'll have ways to reproduce this even if you forget the trends on a test. Here's a table of different electronegativities. You may use it if you want. I would just remember the trends, and then you're good to go. Hydrogen's less electronegative than pretty much, nitrogen, oxygen, sulfur. When I think of a hydrogen-phosphorus bond, I do think of it as being polar, even though they have the same electronegativity. I don't know if that's wrong. It might be. You'll actually, if you go online, you'll actually find multiple different scales of electronegativity. There's an empirical one that's based on just taking an average of electron affinity and electron ionization energy, both of which can be measured independently. Linus Pauling came up with his own scale, just, I guess, using his mind and his own subjective thoughts about what chemistry actually are. And his are out there too. These might be his. I don't know which one's which. So bear in mind, different people have come up with different ways to express electronegativity. It is not a directly observable phenomenon, right? It's not like ionization energy where I can actually tell you what minimum energy of light I need to zap a particular element with before I start seeing electrons expelled from those nuclei. This thing requires that you come up with some way of indirectly measuring it, or that you come up with some weird average of polarities based on different bonds. So it's tough. This is how you write a dipole moment. So you draw a dipole is a charge separation. So if you have a positive charge and a negative charge separated by a distance, that's a dipole. And you can write it by writing a plus, or like the tail end of an arrow, at the positive end, and the pointy end, or the arrowhead end of an arrow, at the partial negative charge. So that's what a dipole looks like. That's how you depict it. And every time there's a polar bond, you actually have a dipole that you could draw overlapping, or at the very crudest, parallel to that bond. The delta notation, as I mentioned before, means partial positive or partial negative charge, and the plus or the minus indicates whether or not it's positive or negative. Make sense, hopefully? There can be multiple dipole moments inside of the same molecule, and you can try to average those out to come up with a total overall dipole moment for the overall molecule, which may or may not be the same as any of the dipole moment directions that you've drawn for any of the bonds themselves. You have to take like an average, and the average might not be the same as the contributors to that average. Yeah. So, do I do water by itself? Apparently not. Let's do water. Let's do the bonding of water and thinking about water, and then we'll actually derive where this comes from. So we live on Earth, right? Earth has a lot of water. It's good to know about water. It's in our bodies. A lot of hedge funds are really interested in water right now. I think they're nuts, but they might be right. I'm often wrong. So this is a Lewis structure for water. Let's talk about the dipole moments here. Which is more electronegative, oxygen or hydrogen? Oxygen is more electronegative. So that means if there's this, for these shared electrons between the hydrogens and the oxygen, each of these bonds is going to have a partial negative charge on the oxygen and a partial positive charge, on each hydrogen. Why am I saying that? I'm saying that because the oxygen is more electronegative, so it is going to hog the electrons that are being shared in these bonds. So that's going to give it an overall negative overall negative charge, partial negative charge, and the hydrogens will have a partial positive charge based on that unequal sharing. And if I had to draw dipole moments on these bonds, I would draw them as like that. So like those are the dipole moments. They point to the negative charge and away from the positive charge. So there you go. The overall dipole moment for this molecule looks like this. So I average those two bonds and those two bond dipoles, and I get this overall dipole for water. So there is a positive end, the end with the hydrogens, and there's a negative end, the end with the oxygen. So this makes water a very, very, very good solvent for dissolving different ions. So a lot of ionic compounds will actually be dissolved by water. And the cations of ionic compounds will be dissolved by the water molecules that orient their partially negative oxygen ends towards the positively charged ion. And then the anions, the negatively charged ions, will have water molecules orient themselves around them so that the partially positively charged hydrogen ends are closer to the anion. So that's why water is such a good solvent. We can do some of these. I eventually will have to show you guys how to do the Lewis structures. I don't know that I have enough time. Do you guys want me to do a Lewis structure example, or do you want me to? Okay, so I'm kind of putting the cart behind the horse. I'm putting the cart behind the horse. I'm being